going to prove the cosine rule, a squared equals b squared plus c squared minus 2bc cosine of a, using the fact that the area of this triangle can be given by the formula b times c times sine of a divided by 2. We'll draw a square whose edges are the same length as the base of this triangle. Then we're going to fit 4 triangles of this size into the square so that the base of the triangles lie on the edges of the square. Because all of the triangles overlap, the sum of areas of the 4 triangles must be greater than the area of the square. If we remove these overlaps, the 4 triangles with the overlaps removed are almost the value of the area of the square. If we add the area of the small hole in the middle, we will be able to express the square in terms of the 4 triangles with the overlaps removed and the small gap in the middle added. And we'd have an equation that looks like this: a squared equals 4 triangles minus the overlaps plus the whole. Let's plug in the value of 4 triangles first. That gives 4 times the area of one triangle equals 2 BC sine A. What we need to do is figure out the area of the overlaps and the area of the small hole in the middle. And once we've done that, this equation should look exactly the same as the cosine rule. I'm going to start by discussing what happens when you take 2 congruent triangles, one placed on top of the other, and then rotate one of them by 90 degrees. Here's the first triangle. I'm going to place a triangle of exactly the same size on top of it, and then I'm going to rotate the first triangle at this point by 90 degrees. Now hopefully you can see that the base of the rotated triangle is now 90 degrees away from the original base, but the left edge also rotated 90 degrees, so the new left edge is rotated 90 degrees away from the old left edge. Since they are now 90 degrees apart, this edge must be perpendicular to this edge. If I duplicate the rotated triangle and then translate it horizontally to the left without rotating it, the duplicate's left edge angle has not changed, but now the left edge of the original triangle and the left edge of the rotated triangle are overlapping. And since they're perpendicular, the angle between them must be 90 degrees. In fact, these are essentially 2 perpendicular lines, which means that this angle in the overlap must be 90 degrees. And because the main triangle edges begin at the same point, the overlap is a triangle. Therefore, the overlap is a right-angled triangle. If I were to add another triangle rotated at 90 degrees, we get the same effect where the bases are rotated another 90 degrees and the left edges of the triangles overlap and are perpendicular. And that must mean that the new overlap must be a right-angled triangle. And once we've added the other 2 triangles, we'll have 4 overlapping right-angled triangles. So let's redraw the square that has edges that are the same length as the base of our triangle. And now let's put the 4 triangles in so that their bases align with the edges of the square. The first thing to note is that since the bases of all the triangles are at the edge of the square and the length of the bases are A, the internal angles of the triangles that are opposite the base must have the value of capital A, because in this triangle the angle A is opposite the edge A. So let's label those. We know that all of the overlaps are right-angled triangles and that the overlaps are at the intersection of the edges, so let's show where the angles are. Also notice that one of the edges inside the triangle is the short edge of the triangle, which is the C edge, so let's label those. The edges of the overlaps that I've just labelled are all opposite to the right angles in each of the overlap triangles, so the C edge is the hypotenuse in the overlapping right-angled triangle. For the other 2 edges, I'm going to call the short edge the base and label it B1, and I'm going to make the longer of the 2 edges the height, and I'm going to call that H1. Let's get the sine and cosine of the angle A in the pink overlap. So sine of A is going to be opposite over hypotenuse, but the opposite is H1 and the hypotenuse is C. Cosine of A equals adjacent over hypotenuse, and that is equal to B1 over C. Now if we multiply both sides of each equation by C, the C's on the right hand side of both equations cancel, so we get that the height of the overlap is equal to C times sine of A and the base of the overlap is equal to C times cosine of A. We can use this to work out the area of the overlap now by using half base times height, and so half base times height is 1 over 2, well the base is C times cosine of A and the height is C times sine of A. Since all of the 4 right-angled triangles have the same hypotenuse and contain the angle A, C sine A must be the height of all the overlaps, and C cosine A must be the base of all the overlaps. So the sum of all the overlapping triangles must be 4 over 2 times this value. So 4 over 2 times the trigonometric value would be 2 times C cosine A, which equals B1, times C sine A, which is H1. I'll substitute the values back in at the end by using these two equations. We can now plug the area of both the overlaps and the 4 triangles into the original equation. 4 halves are 2 and C sine A equals H1. So this will become 2B times H1. We can plug in the overlaps, so we subtract 2B1 times H1. And now we have an expression for the 4 triangles minus the overlaps, and we only need to find the area of the remaining whole. In order to calculate the area of the whole, which is a quadrilateral, we need to figure out the length of each side. But notice that each side of the whole is sandwiched between a short edge of the right angled triangle and a long edge of a right angled triangle. But all of these edges are aligned along the B edge of the triangle. This means two things. Firstly, it means that all of the edges of the whole are the same length, but it also means that we can express the length B as the edge of the whole plus the base and height of a right angled triangle. And then if we subtract the lengths either side of the edge, that will give us the length of the edge. So that gives us that B equals, well, there's the edge of the whole, let's call that EH for edge of the whole, plus the base of the right angled triangle, which is B1, and plus the long edge of the right angled triangle, which is the height, which is H1. We want to subtract both of these from both sides of the equation. It will just leave the length of the edge of the whole, so that's B minus B1 plus H1 equals the edge of the whole. Each of the corners of the whole are at the point where two B edges intersect. The intersecting edges are perpendicular, which means that all of the corners in the whole are 90 degrees, so the whole is a square. So if we want the area of the whole, we just have to square one of the sides EH, and that means squaring the expression on the left hand side, and that will give us the area of the whole in the middle. And now we can plug the expression in, and we have the A squared area expressed in terms of the 4 triangles, the overlaps removed, and the whole in the middle. And now it's just a matter of computing what's in the brackets, simplifying the results, and seeing what we get. Let's expand the brackets. I assume you already know how to expand the brackets, so let's just do it the shortcut way. That's going to be B squared minus 2 times B times B1 plus H1 plus brackets B1 plus H1 squared. We'll expand the simple brackets first, so that gives us B squared minus 2B times B1 and minus 2B times H1. And that's added to the squared brackets. B1 plus H1 squared is B1 squared plus 2B1 times H1 plus H1 squared. And now everything's expanded, we can simplify by cancellation. At the beginning of the expression we have a 2b times h1, but we have a minus 2b times h1 here, so they cancel. Then we have a minus 2b1 times h1, but we have a plus 2b1 plus h1 here, so these two cancel. That leaves b squared plus b1 squared plus h1 squared, and minus 2b times b1. We can replace the b1 here because b1 is c cosine a, so this is minus 2b times c times cosine of a. Bring down the b squared, and that just leaves us to figure out b1 squared plus h1 squared. But remember, b1 and h1 are just the base and height of the right angled triangle overlap. The hypotenuse was c, and by Pythagoras, b1 squared plus h1 squared equals c squared. So this part of the equation, b1 squared plus h1 squared, can be written as c squared. So we add c squared, and so we get that a squared equals b squared plus c squared minus 2bc times cosine of a, which is exactly what we were trying to prove. This is the cosine rule, and we're done. So thanks for watching.